Alright, so we're going to start talking about different types of transformations. This entire half of the unit is all about transformations of figures, lines, points, planes, things like that. So this is going to be very conceptual things. You have to think spatially. This is not algebraic, okay? So I know some of us prefer algebraic things. We were really good at algebra. This is not it. This is going to require you to think spatially and conceptually. So I would definitely study this stuff up until that Unit 2 test, okay? So make sure you just, if you're not good at thinking spatially, memorize at least the rules to help you get the correct answers. All right, so first, our definition for transformations, which is what we call mapping, is in a plane. A mapping is a transformation if each pre-image point has exactly one image. And each image point has exactly one pre-image point. In other words, every point that was originally in the figure has to have some new point in the transformation. They all have one that they go with, all right? Okay, so that means that your new figure, so the one that's recreated after you make the transformation, is going to be referred to as the image, while whatever you had originally is going to be referred to as the pre-image. So if they have already drawn both for you on the graph, you have to know what pre-image and image means because that's how they're going to refer to them. So the pre-image would be the original, image is the new, what happened after they moved it. So these are some types of transformations that we're going to be talking about. First is dilations. So dilation is going to mean that you either enlarge or reduce the size of something. So it's going to stay on that same scale. It's going to be the exact same figure, just growing larger or smaller based on the original. Okay? The second type of transformation we're going to talk about is rotation. This literally just means to turn the figure, right? They may ask you to rotate it 90 degrees, which would only be half the way, like sideways, right? Or 180, or maybe even 360, all the way back around. But rotation does just mean to turn. Our translation is to basically slide an image somewhere. Okay, so you could slide something left or right. You can also slide something up or down. They may also ask you to slide it to the left and down, right? So that would mean sliding it both directions at the same time, so maybe almost diagonally looking. And then we also have our reflection. Reflection is different than rotation because these should be a mirror image of each other. All right, if you folded your paper in half, it should all match up, okay? All right, so right below here, there are a bunch of different drawings, A, B, C, and D. They want you to look at those drawings and determine if you think that those drawings show reflection, rotation, or translation. Okay, so I'm going to give you a second. I want you to look at A, B, C, and D. Below each picture, I just want you to write what you think that is showing. Okay, so I'll give you just a second to do that. Okay, so on figure A, what did we say happened there? Rotation, right? Good. So it was the same lightning bolt. It was tilted kind of to the side a little bit, and they just rotated it up some, right? Okay, what about figure B? So this one's a little bit tricky. You have to pay attention to the where the door is, right? So what do we think this one is? It's also a rotation, right? It's not a reflection because if I folded this in half, the doors aren't going to meet up, right? So it's not a mirror image. This one is also a rotation. Good. All right, what about C? What did we say C was? Translation, right? It just slid it up. Good. And what about figure D? That one is reflection, right? If I folded it in half right there, it would all match up. Very good. All right. So the second term we're going to talk about is isometry. And isometry occurs in a plane. So in this plane, an isometry is a transformation that maps every segment to a congruent segment. This can also be called a congruence transformation. So basically, in isometry, they're saying your figure can't change size. Everything has to still say the exact same size. So there are some of our transformations that will not show isometry, right? Like dilation, things are getting bigger and smaller. They're no longer congruent. So on these four examples, you're going to look at them each and decide if they are showing isometry. If they are, write the word isometry beside them. And then, if it is, you're going to name what transformation it is showing as well. So you'll name isometry, and then you're also going to tell me which type of these from up above it is. Okay, on A, did that one show isometry? No, because that was what type of a transformation? Good. All right, what about the stars? Did that one show isometry? Yes, because it was what type? Good. Okay. It could be that they just rotated it. Could it also be something else? It could also be reflection, right? If I folded it right here along this line, everything could match up, right? All right, what about C? It is isometry. And this one would also be reflection. Good. All right, and what about the ants? Dilation as well. All right. Okay, if you'll flip it over onto the back of that page, we're going to talk about translation. All right, so translation is the result of a movement in one direction. It can also be the end result of two successive reflections. Okay, and successive just means one after another, right? So if I was to reflect something maybe across the y-axis, but then I reflect it across the x-axis, it could appear to be the exact same image that looks like it was slid over and down, right? Okay, so the properties of your translation are going to be first that it always preserves congruence. So the size of your figure and the shape of your figure will never change when translating. It's also going to preserve the orientation of the figure. And remember, orientation just means which way it's facing, right? Kind of like that house on the first set of examples we did, right? Whenever it was rotated, it lost its orientation, right? It changed directions. Okay, a translation is a transformation that can be described in coordinate notation in the following way. So we have our coordinate x, y, right? If I am translating to the left or to the right of my current x value, I'm either adding or subtracting some number to it, right? Okay, we refer to the number that is changing your x as h. So you have some x plus h. And if your y value is moving from its original location, it's moving up or down. So your value that changes your y is referred to as k. Just like it is when we're talking about our parabolas, right? Whenever you're talking about transformations of those. So every point shifts h units left or right, depending on if it's a positive or negative. And k is going to shift up or down, depending on if it's a positive or a negative. All right, so in this next example, it says to find the coordinates of the given figure, then find the coordinates of the image after each translation. Okay, so first we need to fill in where coordinates A, B, C, and D are. So where is point A on the coordinate grid? Good. And where is point B? Good. And where is point C? 1, and where is point D? Good. Okay, so these are the original points, right? Okay, they ask us to then find A prime, C prime, B prime, and D prime, right? So that means I'm going to move them, right? If we call them prime, it's the new image, or the image, right? And then this would be considered the pre-image, is what we called it. All right, so on example number 1, they say you're going to add 3 to all of your x values, okay? So if I add 3 to negative 3, what's the new x value for A? 0. And if you add 3 to 0 for B, what's the new x? 3. And if you add 3 to 1 for C, you get... And if you add 3 to negative 4 for D, you get... Good. All right, for Y, they say we're going to subtract 5 or move down 5 units, right? So if I subtract 5 from 3, where do I land? Negative 2. And if I subtract 5 from 3, again, we land at... And if I subtract 5 from 1, I'm going to land on... Right, and same for point D. All right, so now that I have these 4 points, I'm going to come over here and graph them. So my first point is A prime, which is at 0, negative 2. And remember, to denote that it's the new one, you put that little prime symbol, right? Okay, B is at 3, negative 2. And C is at 4, negative 4. And D is at negative 1, negative 4. Okay, and what they meant by our definition on that front page that every image, pre-image point has an image point, and every image point has a pre-image point, I can literally map them, right? A became A prime, B became B prime, C became C prime, and D became D prime, right? It each had a point to map to in the new figure, okay? All right, so now for number 2, we're starting with the original xy. So I go back to my original points A, B, C, and D and make these changes. So it says that we are going to subtract 3 from all of our x values. Okay, so my A was -3, now it's going to be good. Okay, and we're not changing the y, right? My B x value was 0. If I move down 3, I'm going to be at good, and we don't change the y. For C, I was at 1. Now I'm going to be at good. And my y doesn't change. And then I was at -4 for point D. Now I'm going to be at good. And we don't change the y. All right, I'm going to come plot those points over here as well. Okay, so I've got, let's see here, -6, +3 is my A double prime. I've got -3, 3 as my B double prime. I've got -2, +1 as my C double prime, and -7, +1 for my D double prime. So again, I'm going to have a point from the original pre-image that maps to this new image. Right? Okay. All right, still based off these same, they give us examples 3 and 4 that we're going to put on the graph down here towards the bottom so that we're not putting them all on top of each other. So that's why they started over with an A prime here, but these ones should be double primes. So we'll add an extra one in there. All right, so for number 3, it says that we're not going to change any of the x values at all. So my x's are still -3, 0, 1, and -4. But I'm going to add 4 to all of the y values. So for A, if I add 4 to 3, where am I going to be? Good. And for B, if I add 4 to 3, again, I'm going to be at 7. And then for C, if I add 4 to 1, I'll be at, and it'll be the same for D, right? Okay, so down on the second coordinate grid, I'm going to plot those points. So I've got a point at -3, 7 for my A prime. I've got a point at 0, 7 for my B prime. A point at 1, 5 for C prime. And a point at -4, 5 for D prime. Okay, and then we just have one more that we need to map. So this last one says we're going to subtract 2 from each x value. If we subtract 2 from -3, that puts us at good. And if I subtract 2 from 0, I'm going to be at good. And if I subtract 2 from 1, I'll be at good. And if I subtract 2 from -4, I'll be at -6. All right, and then I have to do the y value. So I'm going to go back and add 5 to each y value. So what's 3 plus 5? A, and that's going to be true for my A and B, right? And then for C and D, what's 1 plus 5? 6. So then I come and plot those points over here as well. So we got -5, 8 is A double prime. -2, 8 is B double prime. -1, 6 is C double prime, and negative 6, 6 is D double prime. Alright, so transformations are pretty easy, not really any rule to memorize, just move as much as they ask you to. Alright? Okay. So flip over onto the next page and we're going to talk about vectors. So it says that another way to describe a translation is by using a vector. A vector is a quantity that has both direction and magnitude or size. A vector is represented in the coordinate plane by an arrow drawn from one point to another. So you may have talked about vectors. Have any of you guys taken physics yet? No, okay. So you'll talk about vectors some in physics that talk about where magnitude moves things. But it says in the diagram, this shows a vector that's named FG. So this green line here is FG, the vector. The initial point or the starting point is at F. We know that because the arrow is on the other end at G, so it's headed towards G. That's what we call the terminal point, the point where the arrow ends up. And then we have what we call the horizontal and vertical components, which is how many units over and up or down you move to get to that next point. So it says the component form of a vector combines the horizontal and vertical components. So the form of the vector FG would be 5, 3. Reason being, we moved 5 units to the right here and 3 units up. What's important to realize is that these are not parentheses on either side of the 5 and 3. They look kind of like our less than, greater than symbols. So that's what differentiates a vector from just a regular coordinate point. Okay. All right, so on example 3, they want us to name the vector and write its component. Okay. Well, what would we call the vector on A? The other one was FG. This one is BC, right? Okay, so this is the vector BC. And we know it's BC because C is the arrow, right? The C has to go on the end. All right. And to get from B to C, am I going to move up or down? Down. And then I move to the right. Okay. Just like in a coordinate point, you list your left and right shift first. So how many units did we have to move to the right? 9. And how many units did we have to move down? 2. So to show that we went down, you put a -2. If we moved to the left, you would put a negative in front of that number. Okay. All right. What would we call figure B? ST. Okay. All right. And then for ST, did we move up or down any? No. Did we move left or right? How much did we move? All right, so we're going to have -8 for moving left and right. And then you guys said we don't go up or down any, so we just put in a 0 for our vertical part of the vector. All right. Okay, this says that the vertices of the triangle ABC are at 0, 3, 2, 4, and 1, 0. All right, so there's the triangle. It says to translate this using the vector 5, 1. So what does that 5 mean that we moved? To the right, 5. Okay, so if A was at 0, A prime is going to be at 5. Okay, so A x value was at 0. We said we moved 5 to the right. Okay, the y value was 3, and our vector says our vertical component is -1. So where is the y value now? Good. All right, for B prime, what are my new coordinates going to be? And 3, good. And for C prime? Good. All right, so then you would plot those points. There's my A prime, and then my B prime is at, did I count that right? 1, 2, 3, 4, 5. Oh, I went too far over. B prime is at 7, 3. And C prime is at 6, -1. So you can see it's still the same triangle, just been translated, right? Okay. Then we have a few examples here at the bottom that say to describe the translation A and B in coordinate notation and C and D in vector notation. Okay, so remember we start out with some original coordinate x, y, right? And then the way they told us on the page before how much we moved was by adding or subtracting some amount to x and y. Okay, so this says I'm going to move left 5 units, so I'm going to put left means minus, so -5. Okay, and then for my y, I'm moving down 3, so I'm going to have good. Okay, so they said to do the same thing for b. Okay, this one says we're moving right 6, so I'm going to have +6, good, and up 2. So I'm going to have, yes, +2, very good. All right, and then on these last two here, C and D, they said we're going to put these ones in vector notation. So remember in the vectors, they don't put the x and y in there, and they use this symbol instead of a parenthesis. Okay, so it says that we move left 7. What would left mean? So I'm going to put a -7, and up 4 would mean a +4. All right, for D, 12 units to the right would mean +12, and 10 units down would mean, very good. All right, okay, we'll have to, all right, so now we're going to talk a little bit about reflections. So one type of transformation is called a reflection. So in the figure below, line M is called the line of reflection. Since P is on the line of reflection, it's a reflected image itself. X is the pre-image. And X prime is the image. So what they're saying is they reflected along this line M. So basically M is like my line of symmetry, where I would fold in half. So X was up here, it has a mirror image of itself down here, right? But since P is on the line, and that's where I folded it, P is also P prime. It's itself, right? It doesn't move off of the line. Okay, and our properties for reflections are going to be that they also preserve congruence. But instead of preserving orientation, it's going to change your orientation. And remember, orientation is just the way it faces. All right, and then our definition for the line of reflection is the perpendicular, remember that's our symbol for perpendicular, bisector of every segment that connects a point and its image. it says to sketch the image of what the polygon would look like after it's been reflected over the given line. So the line with the arrows is like your line of reflection. They're saying sketch what you think it would look like on the other side. Well, it should be a mirror image, right? Point A should have something that matches it pretty much in the same spot over here that we would call A prime, right? So those map to each other. Point B should have something pretty much just like it over here that we would call B prime. And then C prime is still going to be on the line just like P was above, right? So if I go in and connect those, it should look pretty similar to the original, right? It should be the same thing for B. On B, they're saying we're reflecting across this horizontal line instead of a vertical line. But that means that D should have a matching point somewhere right here. And C is going to have some reflected point right here. And then B is going to have some reflected point down here. And A is going to have some reflected point down here. Okay. So they each had a matching point below that was in the same spot just across from it, right? Okay. In the next section, they ask you the number of lines of reflectional symmetry that each one of these have. So basically they're asking, how many lines could I draw where I could fold this shape in half and everything would still match up? Okay? So on figure A, how many lines could I draw? One, right? It would have to go right through the top here, right? Okay, what about on figure B? Two. Okay, what about on figure C? Four. So I'm hearing 2 and 4. Where do we think that the first two would be?
Horizontal and vertically.
Horizontally and vertically, yes, of course those would work, right? Where are we thinking the others could be? Okay, so this is a rectangle, right?
Oh, it's a rectangle. Unless it's a square.
They didn't match up, did they?
Yeah.
Oh, yeah.
Right?
Austin.
So only 2 on that one. Okay, what about D? How many do we think on D?
1.
5.
1. Oh, 5. Yeah.
Right. If I draw this 1, if I turn my paper, that's still the same shape no matter which way I turn it, right? So I could also draw it through this top, if this was the top point. I could draw it if this was the top point, or if this was the top point, or if this was the top point. All right. Okay. We're on the last little bit here. It says, find the reflection image of each point in these. Okay, so first we're going to reflect over the x-axis. I'm going to call these points A and B. All right. So I have point A at 3, 5. Okay. If I reflect that across the x-axis, which is the horizontal line here, where do you guys think that should end up? Okay, negative 3, 5 would be over here. And I said I was reflecting it across this line. You need to come down. The y should become negative, right? So there would be my A prime. So same point, just the y became negative so that when I fold it in half, it matches up, right? Okay, if I had a point at negative 2, 1, where's that one going to be? Negative 2, negative 1. Good. So all that changed here was the sign of y, right? Okay. Let's come over here. I'm going to call these points C and D. So I've got a point at negative 4, 2. And I'm supposed to reflect it across the y-axis. So this time I'm folding it across this way. So at 4, 2. Very good. All right, and then D is currently at 3, 1. Where would D prime be? negative 3, 1. Very good. All right. Okay, easy enough there. All right, let's flip it over onto the back. Last two. Okay, it says given the points M, I, L, and K, reflect it across the line y equals x. So where would the line y equals x be? What does the line y equals x look like?
Just like the parent.
Yeah, just the parent function, right? So it goes through here like this. So if I'm reflecting it across the line y equals x, I'm basically reflecting it across and down, right? Okay, so in this case, whenever I reflect it across and then I reflect it down, it's starting in a different spot than when I put it here, right? So basically, if it started here and it ends up here, if I reflect it across this line, I have switched the x's and the y's, right? Okay, so in this case, anytime I come up with a new point, I'm just flipping where the x's and y's are located. So my m prime, if I switch 0 and 0, it's still 0, 0. Okay, for my I prime, if I switch the x and y, what's the coordinate now?
0, 4, 4.
Good. And L prime would be,
3, 2.
and K prime would be
Negative 3, 2.
negative 3, 2. All right. Okay, on D, if I'm given these 3 points and then they ask me to reflect about the line y equals negative x, that flips it this direction, right? Okay, so still the same idea. I'm switching my x and y, but I'm also going to need to make them negative, or if they're already negative, change the sign, right? Okay, so for my t prime, I switch their places, right? And I change their signs. Well, 0 would still be 0, but negative 3 would become,
3.
right,
Change both signs.
change both signs. All right, for I switch their places,
Negative 2, 2.
right, so it actually still looks the same, right? Okay, for A, what would that one be?
0, 3.
0, negative 3, right, because we got to change that sign. And then for N, negative 4, 1. Very good. All right, so in other words, we are now going to fill in what our rules for reflection are. So this part is super important if you're not someone who can visualize things when we start reflecting later on, that you have this part memorized, okay? So anytime we reflected over the x-axis, what did we change about the original coordinate point?
Opposite y coordinate.
Change the y. Very good. So we left them in their same spot. We just changed the sign of y. Very good. All right. Whenever we reflected across the y-axis, what did we change? The sign of x. Very good. Okay. Whenever we reflected across the line y equals x, what did we change? What did we do?
Their spots like y.
Right, we flip them, right? It becomes yx, basically. And when we reflected across the line y is equal to negative x, what did we do?
Negative.
Right. You got to change the sign of both and switch the places. So those would be our rules for reflection. All right?
Can you stop?